All right, so systems of linear equations. Systems of linear equations are something that you covered in Algebra 1. It was actually, if you remember from your Algebra 1 class, if you had year-long Algebra 1, it was in the fall of that year. I can't do it right now. I got class. Okay. So actually, when I teach year-long Algebra 1, we do systems of linear equations sometime around November is when we did that. So if you had semester version of Algebra 1 with Coach Mack, that would be sometime during the first 9 weeks that you do that with him. So systems of linear equations is something that you've seen before, may not necessarily be something you remember how to do well, but we're going to try to review some of that material today and get you there. All right, so the first thing we want to talk about is checking a solution. Okay, so the question, and I'll call this example A. I tend to letter my examples instead of number them. Example A is 3, -2, a solution to the system. Okay, and here's our system. Y equals 2x minus 8 and 3x plus 4y equals 1. Okay, so here's our system of equations, two unknowns, x and y. What do we know that this 3, -2 is? What's that called? A coordinate. Another name for that is what? Coordinate is correct. That's one name for it. 2 blanks. Ordered pair. Okay. So if you say coordinate, that's that. That's what 3, -2 is. If you say ordered pair, it's the same thing. So no, if somebody says, some of us say coordinate, some of us say ordered pair, they're the same thing. They're synonyms to one another. Okay. So if that's a solution to that system, what does it mean happens with that ordered pair or that coordinate? Anybody remember? It'll substitute for x and y. Which one's x and which one's y? Yeah. 3 is x and -2 is y. So those are x and y. So if we plug that in, -2 equals 2 times 3 minus 8. 6 minus 8, is that -2? Hey, it works in the first equation. Does that mean that's a solution to the system? Not necessarily. It means it's a very good candidate. In order to be the solution for the system, where does it also have to check? In the second one. So you got to plug it into both of them to determine if it is a solution. So 3 times 3 plus 4 times -2 equals 1. Okay. So 3 times 3, 9. 4 times -2 is 8. -8, excuse me. What's 9 plus -8? 1. Does 1 equal 1? Yes. So is 3, -2 a solution to that system? Yes. We answer that with a yes. This is the proof that that is true. Okay. Yes is the answer to the question, but the proof is in showing me that you plugged it in and it worked in both equations. For it to be a solution, it has to work in both equations. If it doesn't work in both of them, then it's not a solution to the system. Okay. It has to work in both. One is not enough. So make sure if you're checking a solution or checking if a coordinate is a solution to a system, you check it into every equation of that system. Even when we get to 3 variable systems, we've got to check it in all 3. So make sure you're doing that. All right. Now, graphs of a system of linear equations. I'm going to take a general approach right here, and then we'll get to a specific example. In general, when you're graphing linear equations, they're done on a coordinate plane. So I'm just going to sketch. You don't have to be too precise here. There's a coordinate plane, and I'm going to draw all three of them. Okay. What are the scenarios for two lines graphed on a coordinate plane? What could happen with those two lines? What's one thing that could happen? If I draw this line and then I have a second line, what could it do to the blue line? It could intersect it. That's one possibility. It would look something like that, maybe. Very infinite number of different ways those lines could go. But they're crossing in how many places? One. So that's one solution. Okay. That's also called consistent and independent. You will hear me say one solution most of the time, but understand that consistent means it has answers. Independent means it only has one answer. Okay, so consistent and independent. That's the mathy word for it. But you're going to hear me say one solution most of the time. All right. Now, what's another scenario for the red and blue line when we graph them? They could be parallel. And what do we know about parallel lines? They never touch. They never cross. They never intersect. That would be no solution. And that would be what's called an inconsistent system. Inconsistent systems have no solution. Okay, so just getting some mathy words that go with this. They sometimes like to use these in textbooks and on different exams that you might have, ACT being one of those. So trying to tie that vocabulary with it. All right, what's the other? There's only one other possibility that could happen here. Could they land right on top of one another? That would be an infinitely many solution. And because it has answers, it's called consistent. And instead of being independent, meaning they only have one answer, it's dependent. Dependent because it has an infinite number of solutions. So here we would have the exact same line twice. The equations would end up, if you put them in slope-intercept form, they would be the same exact equation and would graph on top of one another, which means they touch an infinite number of times. How about that? Now, as we get into three-variable systems later on this week, we'll see that these same three scenarios are going to carry across no matter how large your system of equations are. Okay, so if you've got three variables, then you could have one solution, no solution, or infinitely many solutions. All of these three cases, if you got two variables, three variables, 85 variables, doesn't matter. These three scenarios are always going to be the case. The graphs look quite different when you're dealing with linear things, but and then nonlinear things. And when you get into three variables, you're dealing with three-dimensional graphs, and that's pretty tough for most of us to draw. But same idea does happen with that. All right. So if we were to look at a system of equations, just a simple graph, and they said name the solution and they drew a graph, and I'm just going to graph it, a fairly easy one, and we're not using graph paper here, so I'm going to point out some things. So I'm going to graph a blue line here, and then maybe this red line like that, and this point right here where they cross is the point 5, 4. That point where they cross. Yes, sir. It wouldn't be a system if there's just one. You've always got to have at least two to get a system out of that. So where they cross, is that the solution to the system? Yes, that point where they intersect is the solution to the system. Okay, so 5, 4 is the solution. Where they cross is where your solution is. All right. Take the same idea, and they asked us to find the solution by graphing. Okay, if we're going to find a system of equations solution by graphing, let's take the equation y equals 3x minus 2, and then x plus 2y equals 10. So there's our two equations. If we want to find the solution by graphing, what do I need to do with each equation? Make sure it's in slope-intercept form, because that's the easiest way to graph. Is it the only way to graph? No, but it's the one we're most familiar with from junior high math all the way up to now. So is the first one in slope-intercept form? Yeah, I got y equals 3x minus 2. That's y equals slope times x plus the y-intercept. So we're in good shape there. And then the bottom one, it's not quite there. What do we need to do to get that there? Get y by itself. So what's the first step to do that? Subtract x, and we got 2y equals negative x plus 10. And then divide everybody by 2. What happened there? Forgot how to write a 2. There we go. So that's going to give us y is equal to negative 1/2 x plus 5. So we have slope-intercept form in the first equation, and now we have slope-intercept form in the second equation. Okay? And if you were going to graph these by hand, for this one, where would you start? Where's your first point? At negative 2. You'd put a dot at negative 2 on the y-axis, and then do what? The slope is 3, so we would go up 3, right 1, right? That's a great way. And then this one, the first point would be where on the y-axis? 5, and then we would count the slope negative 1/2, which means we'd go down 1 over to the right 2. Okay, so that'd be graphing it by hand. Just definitely something you should know how to do and be able to do. I'm going to graph it with the graphing calculator. So if you've got your graphing calculator, I'm going to try to use it today. So I'm just turned it on, got to the original page there, and if we want to graph something, then we need to be in the y equals menu. So you hit y equals, and it should take you here. If you have equations in there already, you might want to delete those. So just go down, arrow down, and hit the clear button, and it'll delete whatever's in there. So hitting y equals to get here, and then we're going to graph those two equations. So I've got 3x, 3, and then the x is right here beside the alpha button, right beside green there. So x, and then minus 2. And then I'm going to press the down arrow to get to the second equation, y2. And I'm going to type in that equation, which was negative 1/2 x. So negative 1 divided by 2, that's negative 1/2 x, and it was plus 5, correct? So I've typed those two equations into the y equals menu. You'll get more familiar with this as you go if you're not used to graphic calculator. It's going to be handy for that. And then we can hit the graph button, which is in the top right corner, the one at the very top and right. And there it graphs the blue one and then the red one. And how many solutions does this system have? One, because these two lines do what? They intersect. We can kind of guesstimate where that's at. It looks like that's 1, 2, 3, 4, maybe thereabouts. Bless you. All right. So that's an estimate. Here's how the graphing calculator is pretty handy. It'll actually find that whole intersection. We can hit second and trace. That gets us to the calculate menu. And look at number 5. It says intersect. So it's finding the intersection of those two graphs. It'll tell you the ordered pair for that. So we're going to select number 5 there. And it asks, what's the first curve? Well, the first curve, because you could have up to 10 graphs on the same page at a time. So it's asking you, which 2 are you looking at? We only have 2 that we've graphed. So first curve is y1. Notice that it puts y1 in its equation up here in the top, so you know which one you're on. I just hit enter. And the second curve, y2, that's the only other equation I have in there. But just be careful to make sure it's on the right one. And it says y2 up in the corner there. Hit enter. And then it asks us to guess. It actually is good to go ahead and move that cursor close to where the intersection is, because as we go through the course, we're going to end up graphing systems of nonlinear equations where you might have a parabola mixed with a line, and those have more than one intersection. So you've got to pick which one you're asking it to find. So just get in the habit of, if it asks you to guess, move to the place where you think the answer is. I think it's pretty close to right there, so I'm just going to hit enter. And notice intersection is at the point 2, 4. 2, 4. The ordered pair, 2, 4. How can I verify that I know that's correct besides a graph? Plug it into both equations and it should work. 3 times 2, 6, minus 2 would be 4. That works in the first one. Plug it into the second one. 2 plus 8 is 10. So we know that that's the solution to that system of equations because it works in both of those. So graphing those, you can graph by hand and get the solutions. You can also graph with that graphing calculator and get the solutions. Be able to graph by hand. Okay? Don't just only be able to graph with the graphing calculator. Be able to draw a graph by hand with graph paper or a grid given to you. But keep in mind, you can always check your graph that you drew with the graphing calculator. It's always a handy thing. All right? So, solving systems by graphing. How do we recognize parallel lines? Good. The same slope, but different what? Yes. Y-I-N-T. I'll abbreviate. Anytime I abbreviate intercepts, I-N-T is how I do that. So just get you used to my thing. So parallel lines have the same slope but different y-intercepts. The same line, easier to recognize because you'll have the same slope and the same y-intercept out of that. So you can tell if two equations are the same. So solving systems by graphing is an easy thing. It's not necessarily the best way of getting there because the calculator rounds things and does decimals a lot of times, and we don't get exact solutions because if it's at an ordered pair that has like 1/3 in it, it's 0.3 repeating. It never can put enough 3s after that decimal to get it exact. So we want to be able to do things algebraically as well. So that's the next step here, is solving systems algebraically. Okay. Algebraically, trying to refresh your algebra skills here in solving equations. That's one of the reasons that we do this early on, is to just get you back to solving some equations. You solved a lot of equations in geometry, I'm sure, in that context. We're just going to kind of get you back going because you've had a summer off at least. Some of you have had since fall of last year off from math classes. So we just got to get you refreshed on that. So when you're solving algebraically, there's two methods that you can use. One of those is substitution. Substitution is substituting one thing into another equation, okay? And substitution is a fine method for solving systems of equations. It's not always the best method, but it does always work, okay? Substitution will always get you a solution if you do everything correctly, or get you a solution that if the system has a solution. So let's look at the example y equals 3x minus 2, and then that same system that we just did by graphing, let's look at it using substitution, because it's a good one for using substitution with. Why is this equation system, this system of equations, why does it lean itself to substitution easily? Because the y is already by itself. Anytime you get a system and one of the variables is always already by itself, substitution may be the faster way of solving it. Okay? So here, the first equation, we've got y already. We know y is 3x minus 2. I can take that 3x minus 2 and do what with it in the other equation? Substitute in the place of that y. Okay, so I'm taking what y equals. Here it's 3x minus 2, and I'm going to replace y in the second equation. And that's going to give me x plus 2 parentheses 3x minus 2 equals 10. All right. Now, what do I do to solve that system? Okay, so what property is that? Distributive property. So we're going 2 times 3x and 2 times negative 2. So that's going to give us x plus 6x minus 4 equals 10. Okay, so we're just doing distributive property there. And then what do we do next? Or what's an option to do next? You don't have to do it always. Yeah, combine the like terms there. X plus 6x would be 7x. And then the next step would be get like things together on opposite sides. So adding, Hayes said add 4. It's perfect. We'd add 4. And then 7x equals 14. Pretty easy one after that. The last step is to do what? Divide by 7. And there we get x is equal to 2. All right. Now, that's only half of the coordinate. How do we get that? We know the answer should be 4, right? For y, but how do we get that? Put the x in. Does it matter which equation I put it into? Technically, no, but which one's the easier one to put it into? One that has y by itself, because you got to do less work. So we're going to take that 2 times 3x, or replace x in there. So y is equal to 3 times 2 minus 2. So that's y equals 6 minus 2. And there we get y is equal to 4. So there's the y value, the coordinate. The final answer is always with a system of equations. If you have one solution, make sure you write your answer as an ordered pair or a coordinate. Okay, 2, 4. That ordered pair is the final answer for a solution to a system of equations. Okay, so if you've got any kind of system, we want to make sure that we're writing our answers as ordered pairs, unless they only ask for one part of it. Sometimes they'll say, find the y coordinate for this this system, the solution to this system. So you only have to find one. Okay, so be careful of that. But most times I'm going to ask you for the full ordered pair out of that, both x and y. All right. So there we see a system of equations that leans itself well to substitution. Sometimes we're asked to do substitution to an equation that might look like this: 3x plus 2y equals 1, and then negative 2x plus y equals 4. So it's not, right there out in front of you saying, hey, do substitution. But they ask us to do substitution on that problem anyway, just to prove that we know how. If we're going to use substitution, what do we need to have in order to do that? We need one of the equations to have either an x or a y by itself. Okay? We're good enough for algebra. We've all been through algebra 1. We should be able to get either of those equations to do that. But which one is easier? The second one. Okay? So that's what I'm trying to model to you, is that go for that path of least resistance and get the easier one done, because it makes it better on you. It's less work. Okay? So the second one, if it's easier to get a variable by itself, what do we need to do to it? Yeah, add that 2x to the other side to get y by itself, and it's just a one-step thing. And there we have y equals 2x plus 4. And now we're back to an equation like we just did. We've got y equals something, and we've got another equation up here. So we're going to take that 2x plus 4, and where are we going to take that? We're going to plug it into the other equation in the place of y. So 3x plus 2 parentheses 2x plus 4 equals 1. Okay. Same song, different verse. Distributive property, 4x plus 8. Still got the 3x in front. And 3x plus 4x, 7x plus 8 equals 1. Subtract 8. 1 minus 8, negative 7. Hope you didn't have to use a calculator for that. Again, try to not use 1 if possible. It'll make your brain work faster. So that'd be negative 1 is x. How do I get y? Plug x in. Does it matter where I plug it into? I could go here to the first equation. I could go to this equation, the original one here, if I wanted to. Or I could go to this one where I've already got y by itself. As long as I didn't make a mistake there, I should be good to go, okay? And I can always check myself after I get the answer and plug the ordered pair back in that I'm going to get. So I'm going to plug in there, y equals 2 times negative 1 plus 4. I'm going into the one that's easier, it's shorter work. 2 times negative 1 is negative 2 plus 4 be positive 2. Won't always be nice integer solutions in here, but for example purposes, it can work out real nice. So ordered pair, negative 1, 2. Be careful to make sure you put x first and y second, because sometimes it's so simple, we'll get in a hurry and we'll put 2, negative 1 as the answer instead of negative 1, 2. And if it's multiple choice, you know they're going to have negative 1, 2 as a solution choice and 2, negative 1 as a solution choice, because they know what kind of mistakes you make. So be careful of that, especially when you're working on Khan Academy, if it's a multiple choice one. They're not all multiple choice, but just be careful of that. Okay? All right, so we've seen a couple of examples of using substitution and it being one solution, but we have other scenarios that can happen as well. What's the other scenarios? We could have no solution or infinitely many solutions. Okay, so we've got to keep an eye out for what does it look like when that happens. We know what the graph looks like. No solutions, parallel lines. That's easy to see. But algebraically, it's not always as obvious at the beginning like it would be with graphing. So looking at that, let's say we had this system, 12x minus 3y equals -9, and then -4x plus y equals 3. And we're still using substitution here, so just trying to all the different scenarios that can happen. If we're going to use substitution here, which equation would be best to solve for a single variable? The second one would be really easy to get y by itself. We're not always going to solve for y. We sometimes can solve for x, but here getting y by itself looks like the easiest method. So that's what we're going to do. So there's y equals 4x plus 3. We're going to take that and replace y in the first equation. We have 12x minus 3 times 4x plus 3 equals -9. So that'd be 12x minus 12x minus 9 equals -9. What's 12x minus 12x? 0x. They cancel each other out. What's left? -9. Does -9 always equal -9? Always. So if all the variables cancel out and what you have left is true, then that's a case where it's infinitely many solutions. Because this is true, that means our answer is infinitely many solutions. Okay. If you had the variables all cancel out and you had something like 7 equals 5, does 7 ever equal 5? Never. So that would be a false statement, which would tell us that it's no solution. Okay? So if there's a variable left, then you've got an answer. If the variables cancel out, that's where you have either no solution or infinitely many solutions. No solution, the statement's not true. Infinitely many solutions is going to be like this one, where the statement is true, where it's the same number on both sides. Okay? So you'll recognize that with the substitution if it's going to be an infinitely many solutions or a no solutions type scenario. All right. Well, let's look at the other algebraic method that we'll use. Elimination. Elimination, I put plural, but elimination, it's my favorite way of doing problems because more of them are like this than they are substitution-wise. I guess I just had more practice doing it. But you get the same answers with elimination as you would get with substitution, which should be the same answers that you would get with graphing. Okay, so whichever method, if I give you some problems, say just solve them, pick the method you like the best. Some of them kind of are easier to do with substitution. Some are going to be easier to do with elimination. Elimination, you're eliminating one of the variables. That's our job. It's just get rid of one. 3x minus 5y equals 10. Let's say we had 4x plus 5y equals 4. This is the easiest of elimination type problems. What do we notice about these two equations? The 5y's are what? Opposites, yeah, because one's positive, one is negative. That's opposites. So if you have opposites on your variables, and they're not, not in slope-intercept form, obviously, either they're in standard form, then that's going to be a great candidate for elimination. Here we have exact opposites, -5 and +5y. So if I add those two equations together, -5y plus +5y, what happens to the y's? They cancel out. They eliminate one another. 3x plus 4x is 7x, and 10 plus 4, 14. And I end up with this easy one-stepper here to finish the problem off. Divide by 7. And x is 2. Now here's a little tougher part, is getting y that goes with that. Not quite as easy on an elimination problem because you don't have something that says y equals. So what do we do with that? Pick an equation, plug it in. Does it matter which equation I use? No. Pick the one you think's the easiest. I'm just going to use the top one there. It'd be 6. Subtract 6. Negative 5y equals 4. And then divide by negative 5. And here we get a fraction answer. Negative 4/5 is y. So we get this ordered pair. 2, negative 4/5. How can we verify that that's the correct solution? Plug them into both equations. If they work in both of them, then yes, it is. We could also graph both equations and see if it crosses or intersects at that point. Because that would be 2 and negative 0.8 in a nice exact spot with a graphing calculator if you want to check it that way. So there's always that possibility. All right. So if we see opposites, elimination's easy. (3x minus 7y equals 10), and then 3x minus 4y equals 4. Do we have opposites here? Not quite. Close. Because what do we got going on with the x's? Same thing there. We got 3x and 3x. I just need one of those to be what? Negative. How do I make one of the 3x's negative? Change everything in the problem, change their sign. What mathematically do I have to do that? Yeah, multiplying by negative 1. It really just changes all the signs, but mathematically that's what I'm doing, is multiplying by negative 1. So I get a negative 3x, positive 4y, and now a negative 4. Do I need to change anything in the first equation? No, because that whole point was I'm trying to get one of them to be negative. Would it have been wrong to change the sign on the first equation? No, works the same way. Doesn't matter which way you do that. So I'm just gonna use the first one as is, and I change the sign on the second one. Once I get there, it's back to add the two equations together. That's the same thing. I never subtract. I always multiply and then add. That way, because reason I do that is because most of the time people that say I'm going to subtract the equation, they forget to carry the minus sign through. Like they would subtract 3 minus 3x, but then they would say negative 7, and then they wouldn't subtract the 4. They'd have negative 7 and 4y together and miss signs. That's why I always multiply and then add. It's the same step though. Hey.
Like on the last one we did, get the fraction just be like a negative fraction instead of the top number.
Yeah, you can put the negative in front of the fraction or with the top number. Technically, with the bottom number, it doesn't matter where you put it there. I usually just put it with top number out of habit because that's what I always do. All right. So Tyler's right. It's just subtraction, but I always use the multiply and add because once we start having to do another number multiplier, then you got to do a little bit more. So here the 3x's cancel out. We're going to get y first this time. Negative 7 plus 4 would be negative 3. And then 10 plus negative 4 would be 6. Do your division. Negative 2 is y. and then pick your poison as far as finding x. I'm just going to go back to the original, first one. Minus 7 times negative 2. 3x plus 14 10. Subtract 14. 3x equals negative 4. And then divide by 3, obviously. Negative 4/3. Okay. Piece of cake. Questions about anything we've done so far? Get me.
Should that be simplified?
No, leave it as an improper fraction. You may have seen mixed numbers in the past. In Algebra 2, most of the time you're going to see things as improper fractions in here. So simplify, if it were like 4/8, yeah, reduce that to 1/2. But if it's an improper fraction, reduce, but leave it improper. Don't change it to a mixed number or a decimal. Yes, ma'am.
I need Calvin Smith to the office, please.
Okay.
Thank you.
All right. Then, what are we on here? Check. Say we have 3x plus 3y equals negative 15. 5x minus 9y equals 3. Okay. And here's a system, and we're asked to solve that system. Let's use elimination just to get the practice with it. It would work well either way, actually. What do we notice here with the x and the y on this one? Y's are already opposite signs, so that's always a good thing to notice, because then you don't have to introduce a negative. Because when we introduce a negative, sometimes
The first equation, the x and y are the same.
they're the same number. True. What does maybe combination of those two ideas, Victoria? All right, great idea. So we got the 3 on the first one, the y, and then the opposite on the bottom one is 9y. We can turn a 3y into a 9y by multiplying by 3. So we're going to multiply that top equation by 3 to get that to happen. And that would eliminate the y's. So 9x plus 9y, and then 3 times negative 15 would be how much? Negative 45, thank you. And then 5x minus 9y equals 3. Okay? Once we have opposites, we add, and 9y's cancel out. Yay. And 9x and 5x would be 14x, negative 45, and 3, negative 42. And that divides nicely, like he meant for this to happen today. How much? Negative 3. Good job. So x is negative 3. Take that and use it to find y. Plug into either equation. I'm going to go to the first one. Not because I have to, but because I want to. Okay. So 3x plus negative 9, negative 15. Move the 9 by addition. Get 3x equals negative 6. Divided by 3. Negative 2 is x. This was y. Dummy. Oh, hold on. I did wrong, didn't I? I did a very, very bad thing. Back up. Start over. Luckily, It's the same problem. You got to miss me making a mistake. All right, so plug that in for x now. Sorry about that, guys. Now, same result, different letter. -6, and then y is -2 by division. Ordered pair, -3, -2. A lot of checks and balances here on the systems of equations there. We ended up with the wrong letter left over, so we knew we did something wrong. Or knew I did something wrong. You probably did it right on your paper already, so it screws up sometimes. It's okay. All right, so let's get to one of the more difficult elimination problems. (8x plus 9y). Not that it's just incredibly difficult anyway, but this is a little more fun. 8x plus 9y is equal to 15, and then 5x minus 2y is equal to 17. Really doesn't bode well for just multiplying one of them by something. You know, we never want to really multiply by a fraction. That's not a good thing. So here's the beauty of it. We get to decide which variable we want to eliminate. And it doesn't matter which one you pick. (8 and 5), what's a common multiple between 8 and 5? Say that again. 30? 8 doesn't go into 30. 40. 8 and 5 both go into 40 evenly. What would be a common multiple between 9 and 2? 18. Okay. Which would be smaller? 18. Okay. So that's how I usually decide. Is I look at the common multiple and I say, okay, which one's smaller? 18 is obviously smaller, so I'm going to have to deal with smaller numbers if I use 18 than I am if I use 40. Is it going to matter? No, it'll do the same.
What are the differences last name?
It will affect what we have to multiply by. Yes, absolutely. Because if we're going to eliminate x's and use 40, we're going to have to multiply one of those equations by what? A negative something. Not necessarily negative 40, but we would have to multiply by a negative. So if I see opposite signs, a lot of times I'll just pick that variable to eliminate anyway, because then I don't have to introduce a negative to the problem. Usually introducing a negative to a problem makes things more difficult because sign changes and it's easy to miss one of those, a sign change. That's a common mistake. So let's eliminate y here and get x first. So we're going to turn those y's into 18s. So in order to turn the first equation to have an 18y here, what do I have to multiply by? 2. So I'm going to multiply the top one by 2, and the bottom one, to turn this into a negative 18, I use 9. Most of the time, it's going to be the number that's in front there. It's not always, but it will always work to do that, okay? So when I do that, top equation then becomes 16x plus 18y equals 30. The second equation, 9 times 5 is 45x minus 18y, and 9 times 17 would be 90 plus 63, which would be 153. And again, don't use a calculator if you don't have to. Do your elimination. 16 plus 45. 61x. 153 plus 30. 183. The 18y's cancel each other out. That's what we wanted to happen. We have 61x equals 183. And it divides nicely. The x equals 3. And then to get y value, we're going to take that and plug it in for x. You could go to one of these equations if you want to, but you're dealing with larger numbers there. So I would pick one of these to work with. It doesn't matter which one, but I would pick one of the originals. I tend to go back to an original if possible, unless I have something that says y equals this or x equals something, just because it's easier and it's less problematic. If I made a mistake somewhere, usually I will catch it there. If I plug in the first one, 24, 9y equals 15, subtract 9y equals -9, divided by 9, y is -1. And what's the final answer? 3, -1. Remember your ordered pair, x then y. That's the simplest part. Don't miss it on account of just putting it in the wrong order. Too easy for that to happen. Okay. Okay, so we've seen several scenarios of elimination where we had one solution, we had a consistent and independent system. If we had to graph them, we'd have found these one solutions exactly the same way. If we'd use substitution, we'd have found them the same way. Okay, so let's look at this last one here and see if we can deduce what's happening. 15x plus 12y equals 11. And then -5x minus 4y equals 8. So there's our system. Let's finish up the day. Well, what's nice about this system? What's good about it? You only have to multiply one of the equations because we can turn, if we want to eliminate x, we can turn a 5 into a 15, right? Easily. Multiplying by what? 3. Do we need a negative? If you use a negative, will you have opposites? If I multiply this by -3, what does that turn that into? It changes it to a positive. So do we need a negative? No, because then we won't have opposites. So only use a negative if you don't have opposite signs already. Since we already have positive, negative, and then the y's are the same way. So if you went to eliminate y's, same rule, you got a positive and a negative. You don't need to introduce a negative to the problem out of that. So if I multiply by 3, to get rid of those x's, I'm going to end up with -15x, -12y, and 24. Oh, man, that's right. Hay said both of them were going to cancel out. That's true. So if 15x and -15x cancel, 12 and -12y cancel, 24 plus 11, 35. What's on the left side? If everything is canceled out, what's over there? 0. Nothing. 0. 0 equals 35. No. So what does that tell us about this system? No solution. Good job. Good job. The mathy word for that is it's inconsistent. Okay? Inconsistent, no solutions, what we'll say most of the time, but tie those words together. If you see the word inconsistent, we know we're talking about a system that has no solutions. Okay, so let's talk about what we've learned today, or what we've reviewed today. Systems of equations, what are the graphing, elimination? Those 3 methods are what we're using right now. We're going to learn another method later this week. Okay, so those 3 are what we're using right now. If you're graphing, what are we looking for? Where the two lines do what? Intersect. Okay? So you can draw them by hand and find that intersection. You can graph them with the graphing calculator, find that intersection. It's got that nice tool that'll help you do that. So graphing is a good option most of the time. I will say not a whole lot.